Hello and welcome to the show. My name's Relevant. This is Do All the Things. On today's episode, a Bugera 1990. We're going to be talking about it, looking at the features. We're going to crack her open, take a look inside, doing a bit of a circuit analysis. If you want to hear what it sounds like, try the next video. The Bugera 1990 is actually a very interesting amp. Why? Because of all the Marshalls out there that have been cloned. Who actually clones the 1990? I did a Mark III clone, but the Dual Reverb, I don't think I've ever noticed any other company clone the Dual Reverb, but that didn't stop Bugera. They obviously saw some value in it. And after playing with this amp, I see some value in it too. The 900, I suppose, is an amp that you might have played a lot in the 90s if you were a serious musician. At one point in time, they'd be one of the cheapest genuine Marshall heads you could get on the used market. Even today, they fetch half or a third of the price of an 800. So why is this amp so underrated? Because, well, it was one of the first Marshalls to use op-amp clipping. Or not necessarily op-amp clipping, but op-amps in general. Here's a quick look at the schematic, and we see triangle, 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 tube, tube, triangle, 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 tube, tube, triangle, triangle. In fact, this amp only has one preamp tube. I know you might think, oh, it's got three. No, it has a preamp tube, a buffer stage, and a phase inverter. Only one of them is actually part of the preamp generating the tone. The rest of it is op amps. All up in front here, literally, it's like the first two stages. I think that's why a lot of people didn't like it. It had a more harsh, buzzy tone, but you know what? That actually makes it great for like heavy metal, extreme heavy metal. Having actually had a chance to play on this thing, you don't need a lot of overdrive. So even if you don't have the best sounding overdrive, that's okay because you don't need a lot of it. The 800 needs a good push. So if your overdrive sounds like arse, your tone you're gonna get out of that amp sounds like arse. This one's gonna be more forgiving to what overdrive you plug into it. But once you add that little bit of overdrive, oh boy, you can play death metal all day on this thing. That's part of what makes a lot of modern metal tones is there's that slight augmentation of silicon in there, either from the op amps that we use to push our front end in the overdrive pedals. Enter the Mesa, classic amp for metal and hard rock tones. But you know, most people plug a bit of overdrive in front of it. And even a lot of other famous high gain amps, even the 5150 with the extreme gain that it has, people had a bit of overdrive to tighten it up. This amp already has built into it some of what people use the overdrives to get that effect for. In fact, it is the introduction to some of that op-amp and diode clipping that really gets that extreme tone. And well, this one has all of it, to the point where it's not necessarily good for more old school type tones. And the Bugera, it seems to be a pretty faithful recreation of it. And it actually has a very similar tone to my Mark III. It's almost like Marshall designed the 900 series with the Mark III. It's like, hey, this sounds pretty good. Let's see if we can do it cheaper, or let's use some of these newfangled op amps that are going around that we have a little bit of in this circuit. And then boom, they were able to come up with a very similar tone without actually using tubes. The fact that we can remove tubes from the circuit and get a similar tone to the Mark III just goes to show how useful the tubes were in there in the beginning. And in fact, it might have been the diode clipping and the rest of the tone modeling in the circuit that was really getting that sound. So we're gonna look at the front. We got the usual affair. We got our two gain knobs, clean and lead. Clean goes to 11, which is funny because none of the other knobs go to 11. All the other knobs only actually go to 9 because you see they start at 1. So lead goes to 22. And really, on today's spectrum, it's not really 22 gain. It's just this thing was so much more gainier, more distortion than the amps it preceded. Is that the correct word? That they just kind of, added numbers on there to illustrate how much more you were getting out of this amp. We've got a global single channel equalization. Presence is actually not our conventional presence. And then, we have our masters. Volume, volume, reverb, reverb. And that's actually a great feature. I don't like it when an amp just has one reverb. If it's gonna have reverb, I like it to be channel independent, because chances are I might want a lot on my clean, but not a lot on my dirty. And it has a pretty good clean tone. And in fact, Marshall doesn't call it the clean channel. They call it the normal channel. And then they call this the boost channel. or at least according to the schematic, which is true because if you crank the gain on the clean, you can get some 800-ish gain structures out of it. We got a channel select switch, which is interesting because it's a push button and an LED that toggles. And in fact, this guy doesn't have normal channel switching. It uses a momentary button instead of a conventional latching button. And in fact, you might find, I thought the reverb was broken on this. It will remember the last used setting independently on the channel. So if you switch to the clean channel and turn the reverb off, and then switch to the dirty channel, the reverb will turn back on if you assigned it to be on. If you turn it off, it will stay off, go to the clean channel, turn that reverb on. As you tick back and forth between the two channels, it will actually remember which setting is specific to which channel. So if you have a situation where you plug in your effects pedal, turn the reverb off on a particular channel, when you go to use the amp later without the effects pedal, the reverb's still gonna be off. At least that's what I found with this sample. You might be like, oh geez, and then you gotta go and get your pedal back to be able to turn the reverb back on. So watch out for that. And of course, much like the 1960 I looked at previously, it's an MDF cabinet with a fragile upholstery finish. So it's gonna look road worn, even if it's never been on the road. Inside is pretty typical to what I'm used to seeing in a Bugera amp at this point. A combination of good, bad, and ugly. Ugly as in like, what's up with all this? They couldn't make up their mind? Did they make the holes oversized? They glued these switches in, wrapped them in electrical tape. Got some nice black PCB boards. They're gonna have slightly harder to follow traces. Mostly through-hole components on this board. And reasonable quality components, at least for a budget Chinese piece of equipment. 105C rated capacitors. Yeah, that's pretty nice. I do believe, yeah, there's no reverb tank on this. It uses a digital DSP reverb, it appears. That would be it there, I do believe. Yeah, because this here is the Infinium module. I explained how Infinium works on an electronic level with the 1960. I found in practice how it works on a programming level. It waits till you're done playing, and then it redetects the tube bias. You know, they've attempted auto bias circuits before, but the biggest hurdle is that when you start playing your amp, the tube starts sucking back more current, so the auto bias circuit would start like trying to pull that down. What the software seems to do is it pulls your bias when it knows you're not playing. It actually, the circuit will have a music on function. And I noticed if you mute your guitar after such and such amount of playing, the lights on the back blink like they're redetecting the bias. And it's also the funny effect where if you change out the tubes with something profoundly different, like say going from a cold running 6L6 to a hot running EL34 that needs way less negative voltage, your volume level drops and it'll stay there for a while. And you'll be like, why isn't my amp working? Why isn't my amp working? And then as soon as you mute the guitar, all of a sudden, the volume level just bursts up. It also seems to wait a few minutes. So I guess if you're going from a hot tube down to a cold tube, you might want to worry that that cold tube's going to run too hot initially. But I wouldn't be surprised if the software has some sort of mechanism in place to detect real quickly if you've changed a tube and kind of defaults it down to a colder setting. Because I have noticed even changing from a cold tube to a cold tube, sometimes initially it's a little bit quieter and then it comes up after. So if your Bugera isn't loud right away after changing the tubes, we could call that normal functionality. So we got through-hole power supply, through-hole preamp PCB, through-hole here, but it seems like a lot of the amp is on this front board because bam, this is where we see the SMDs. Generically, a JRC 074, which is going to be a TL 074, TL 072, TL 072. Oh, look at this. PreEQ, Bugera PreEQ. The PreEQ amp. Oh yeah, bud. The DSP reverb on this thing actually sounds pretty good, so I don't hate it. At first I'm like, oh, it must not have reverb, doesn't have reverb tank. Notice the reverb knobs. I'm like, where's the reverb tank? There's no reverb tank. Is it inside? Okay, oh well. It's very quiet as a consequence because there's less signal chain. In fact, it's dead silent, this amp. They pretty much did a good job in that respect. So how does it compare to the actual 800? Well, you see, I don't have the Infinium schematic, but there's going to be minor differences in that. The preamp board is essentially the same. Especially, I've had the opportunity to compare Infinium schematics and non-Infinium amps. and I found, oh yeah, they're pretty much a lot of these are the same position. So, circuit analysis. From the input, it goes into these two op amps, but this is a division. One is the clean channel, one is the dirty channel. And the dirty channel has this very interesting arrangement here of this little capacitor, this little resistor, then a 4.7K and a 47N to ground. Where does that look familiar? I'll tell you where that looks familiar. The DOD 250. We have a 1 meg, a 120 PF, which is actually a 2024 in modern iterations of the pedal, a 0.05, which is effectively a 47N, and then there's your 4.7K. And instead of a direct connection to ground, that is where we set our gain. This feedback loop here determines the gain that this pedal's going to operate at, which means this feedback loop here is determining the gain of that first stage. So what if we wanted to hot rod this amp? Because like I said, it just needs a little bit of overdrive. We could maybe consider increasing the value of this resistor so that less feedback signal can get around. Or we could consider maybe lowering the value of this so a little bit more of it's bled to the ground. We could maybe consider setting this up like a DOD. It's right there. It's like the similar layout as the DOD. Like, that's an interesting concept to me, just to give it the front end that extra little bit of push. Now, here is where we see one of the first differences. If I look at the 900 schematic, which is damn near almost identical, this is the same, but coming off here, we have a 0.22 and then a 10K. On here, they have a 6.8N or a 0.68, so it's a bigger cap, gonna let more low end through, and then a 3.3K. Everything else past here is pretty much identical to the 900 after going over these schematics next to each. One of the only differences being how they lay it out and how they do switching. Well, the layout is in the drawing itself, not necessarily the circuit. We get the second gain stage, and then here we got, a 1 meg potentiometer dictating our feedback. You turn that down, let more feedback through, lower resistance, that's gonna be quieter. We turn that up, less feedback, less gain suppression, more drive. Here is where we see the first change. We have this little switch here. The relay, it seems to be the default resting position is to the clean channel, and the relay energizes to turn on the distortion channel. This is going to be the resting position, which is ground. Pretty much, they're grounding out that circuit if you're not using it. And then boom, we have our first diode clipper, just clipped onto the signal line. Marshall does it the same way. There's the ground, there's the diode clipper. They use a woof 5 bridge there, as I'm calling it, a woof 5, a woof bridge. But it's basically a bridge rectifier. It's gonna have 4 diodes. So this is just their way of doing it. This is functionally exactly identical. Now what's interesting is this right here. Does that circuit look familiar to you? It looks very familiar to me. It looks a lot like this circuit here. That is your tone stack. Your treble, middle, bass. Treble, middle, bass. They have a tone stack in the preamp circuit. It's a PreEQ, and it's on both the Bugera and the Marshall. Here it is on the Marshall. They built in a little EQ circuit, but with fixed positions and some different values. 22 is normal. 110 might reflect the settings you might dial in. There's a bit of 4.7 to ground. That's going to be a voltage divider against that, I suppose. The slope resistor is usually much higher. That's a 4.7. In an actual EQ circuit, you'd see like a 47. Normally more like a 33. And then over here, a 4N7, or that would be a 0.0047. Or 4700p, whereas that might be a 470p normally. So that's way lower, that's way bigger. I guess they pre-EQ it. And then we have this stage here, which is interesting because it looks like we have 3 gain stages, but we don't. If you see the feedback, it's 10K. This thing's running real cold. It ain't clipping or nothing. Also, it's coming after the tone stack, and a tone stack normally kills your signal. If you have it earlier in the preamp, you're not gonna get a lot of gain out of that circuit. Basically, this is a recovery stage. So we're having clipping generated here in these 2 op amps, which is entirely possible. It's entirely possible. I've played with dual op amp circuits that pump out quite a bit of clipping. And then once we hit this, which is gonna kill signal, because basically these diodes, when they hit their cutoff and they fire, they ground out the circuit, you have a significant signal drop, at least 20% off the top of my head. Once you run it through a tone stack, that drops the signal too, quite a bit. So we would have a weak signal coming out of there, boom, buffer, we boost that pupper back up, And then assuming the relay is over, oh, what happens? It drives into a cathode follower circuit. And that's what's interesting, because past here, the circuit's very similar to the Mark III, other than the fact that it has reverb and they have support circuitry for the reverb. But basically, let's look at the Mark III real quick. What is the Mark III doing? The Mark III is doing gain stage, diode clipping, cathode follower. The 900, gain stage, diode clipping, cathode follower. They kind of put the buffer, they tucked it in down over here. Now, as far as I know, you also get clipping out of this. When you drive this section hard enough, that introduces more distortion. It's kind of like the icing on the cake of your distortion texture. So maybe that's the trick here. Marshall found that to get enough of that authentic tube tone, you just need to put some tubes near the end of the circuit, drive them to get those harmonics content that they offer. But, you know, the beginning of the circuit could just be op amps. Op amps don't necessarily have bad clipping tone, just it'll be different, and too many of them, it doesn't really have the depth that you're gonna want. Now, one thing that I notice about this cathode follower stack that I haven't really noticed in many other amps, if any, is this 220 here. So if you know tubes, you know that signal goes in here, the signal that comes out of here is out of phase. However, the cathode follower takes from the bottom. That's going to be in phase with the input signal. So the signal coming out of here is out of phase with the signal coming here, and then we have a little bit of that out of phase signal leached back into the input. That's a feedback loop. This is what they call in tube terms local feedback. So unlike in the Mark III and unlike in many other amps, they are actually suppressing this cathode follower a bit. And it makes me wonder why. If we remove that 220K, what difference does it make to the tone? Going from there, we have our tone stack. This is very similar to the Mark III, except the Mark III uses 47K there. An 072 is also what Marshall will use in their effects loop buffers. That's the buffer for the send, our return, our levels are tandem, op amp, recovery for the effects loop buffer, and then they drive it into a tube again. Now at this point, I don't believe these tubes are going to be clipping, or maybe if you drive the circuit hard enough, usually after your cathode follower, you're done generating distortion, and also after your EQ. And who knows, maybe these clip a bit too. You'd really have to probe it to test and find out. So we have some form of buffer. Usually they call that like a recovery stage or something, a term I forget. And here's where the presence is. Instead of having it on the phase inverter, they've introduced it here. Okay, so there's a capacitor. It's kind of similar to how it might be done on a phase inverter. Even on the phase inverter, they attach it to the cathode of it. So I guess I could see that. Sometimes cathode bypass caps can change the frequency response of a tube in the sense that, you know, the tube's pulling power from here, and that power is going to be agitating based on the frequencies that are going through it. And a resistor isn't going to suppress any particular frequencies. But once you add a cathode bypass capacitor, it kind of, you know, a capacitor doesn't lower potential like a resistor does, so it will let more energy through it, if you follow what I'm saying. However, a capacitor will resonate at a specific frequency. So the energy it lets pass through it is within a specific frequency range, and that causes your gain stage to be more sensitive to a certain frequency. If you try to pump signal through it that's out of the frequency range of that capacitor, it's going to run at the gain set by the normal cathode resistor. But then as soon as you hit a frequency or you're playing something that resonates with that capacitor, then it gives it a little boost of gain in that range. To put it into layman's terms anyway. Past this stage, oh, okay, well, it's part of the reverb send circuit anyway, yeah. However, I don't know what Marshall actually does for their reverb because, oh, well, actually, hold on. There's the reverb tank. They have an op-amp reverb driver connected off that same buffer. My schematic for the 1990 doesn't show what they do for the reverb. So I guess that goes out to the DSP module. Returns here. Then we have our relay selectable for our reverb knobs, whichever channel you're on. That 2.2 meg resistor couples these two situations together, which is one reason why we need a recovery section, because that's going to kill signal, and I assume whatever's going on here is going to kill some signal. But then, yeah, a recovery buffer. Guaranteed this one isn't clipping. There's going to be too much losses at this point. This isn't going to be introducing anything really to our distortion texture. That third tube in the circuit, I consider it a buffer tube, and much like your power tubes and your phase inverter, if you're not cranking the amp to distort everything, it's going to affect your final EQ. So you can use that tube, you can roll it out in such a way to give you a little bit more flexibility over your amp's final overall sound, but not necessarily your distortion texture. From there we go down to this silly situation here, because it's interesting that they did this. They simulated the way Marshall does the master volume on both the Mark III and this amp, where it's op-amp buffered. But Marshall did that for a more different reason. So the signal splits, goes to the two different op amps, but you're gonna notice there's no relay. The reason why is you see this special pin right here? This is a switching op amp. The part number they call it is an M5201. And the funny thing about it is it must have not been a popular thing because I can't find one. You can find some NOS units, but if you go to Mauser or DigiKey and try to find a switching op amp, I can't find a modern equivalent of it. Basically, this signal tells the op amp to turn on or off, and to the best of my knowledge, it's a toggle function. It will switch between the two different op amps, turning one off and turning the other on based on what signal input is on here. So it, as I understand, was designed to be a kind of solid state relay for audio signal switching. A lot of ways of switching audio signals with solid state methods, you know, apparently JFETs can do it pretty effectively, but they will affect the tone. An op amp is part of the circuit, part of the tone. So as a consequence, if we can make one that switches, then we can kill two birds with one stone. We can have our circuit that's doing our amplification, but then also use it as a switching mechanism at the same time. And that's what Marshall did with this amp. They also used it in the Mark III for the master volume. But as you can see, we got signal coming in, signal going out, and our actual volume control is setting the gain. So I guess if we max this out and we have a full feedback loop, it cancels it out and it can't work. And then as we turn that up, it increases the gain and then allows passage. Marshall does the same thing on their channel switching out front. So here is the dirty channel, boost. This is that op amp's not doing anything, but there's the boost, here's the clean. And all they do is they use these switching op amps. So there's no relays in this circuit. They just literally, the op amps will switch on and off which channel they want or don't want. Bugera, because you can't get these op amps anymore and they're using generic TL072s, in order to get the same effect, they have to use actual relays and they have to use a ground to cut signal from the lead channel. So that's funny that Marshall uses these dual purpose op amps. Now, according to my research, this op amp is functionally identical to the 4558, the famous other. If the 7.2 is the McDouble, the 4558, I don't know, the McChicken, that's just how freaking common it is. And that also, something I find very interesting about this circuit, because I have a 4558 and I have a TL072 and I have pedals that I can swap between them. It's compatible. They have different sounds. The 7.2 has a flatter, smoother sound, which is probably why Marshall uses it in their effects loop. It's going to be better for transparency, whereas the 4558 has more, it has more of that mid grind, which makes it great for an overdrive. Probably one of the reasons why the Tube Screamer's famous for it. Just looking at paper, without actually hearing these two amps side by side, they have to have different distortion characteristics. They have to. They're using different op amps, and a lot of them. So much the same way, we have our clean channel coming off here. We have a very similar first stage, 100K of feedback, 15K to ground. So it's suppressing less ground. What happens is you have this feedback here, but when you ground out the feedback loop, it's grounding out signal, which also suppresses the amount of signal passes, which is less feedback and more gain. So by having a greater value ground resistor here, we're grounding out less signal, we're getting more feedback, we're getting less gain out of this. And part of the reason why we have this with this capacitor is, as mentioned, that capacitor is going to resonate. So it's only going to react to certain frequencies that are passing through here. So this is a way of controlling what frequencies get amplified. And often this 4747, same with the 250, it's used so that some of the low end gets rolled off. So basically what this guy is doing is it's grounding out high frequencies that are attempting to go through this path. By doing that and letting more low frequency pass through here and actually make it to the op amp, it causes the op amp to suppress more low frequencies and amplify more high frequencies, if you can follow what I'm saying. And then of course, this is going to be suppressing extreme high frequencies. Because again, this is potential. This is going to be resisting signal that tries to pass through it. This isn't, but it's only going to let certain frequencies pass through it. So this is going to let very high frequencies, 20p is going to let very high frequencies pass through it. Basically crap you probably can't even hear, don't need for your guitar tone, are just going to go directly through this feedback loop, causing the op amp to just suppress, cut those frequencies right out. Then, boom, to the best of my knowledge, from what I recall, this is all the same. Now the rest of this kind of gets interesting too, because once again, we have another op amp buffer here. That's the second stage. One stage, two stage for the dirty channel, one stage, two stage for the clean channel. But the feedback loop is quite a bit different. So we have a maximum of 250 kilobytes of feedback. So that is going to suppress more signal than, you know, say a 1 meg is going to do. We even kind of have a bright cap here. I haven't put much thought into how that affects things. But then we have a bunch of LEDs. That's a form of diode clipping. Some feedback stages on op amps will put the diode clipping here in the feedback loop. So I guess when the signal reaches a certain potential, an LED can kick on, let the signal go directly through, causing this op amp to momentarily just kill that signal and just give it an aggressive tone. But it would have to be proportional to the rest of what's going on here. So it's interesting, even though it's the clean channel, they have some diode clipping on it. But then again, Marshall calls it the normal channel because it does offer clipping and distortion. This is a less aggressive form of diode clipping than this is as far as signal level goes. This is going to affect how the op amp amplifies, whereas this just straight out kills the signal that it's designed to suppress. So as you can see, we don't have the same recovery stage that that other channel has. And well, we don't need it. We also don't have a PreEQ. So this channel is going to sound more natural. From there, boom, we hit the relay, and then the rest is history. History is in, I already discussed it. Now, if we go down where we last left off over here, that is the master volume section, goes through a relay. Then we have this weird JFET arrangement, and I'm not exactly sure what this does. That goes there, so whatever turns this on, it would just straight up mute this, wouldn't it? Certain solid state tech I'm not 100% on. See, reason why I can't figure out what this does is I haven't yet figured out where the other side of this trans connection is. There are certain things missing from this schematic. So now the funny thing is, if we look at the Marshall schematic, we might get confused in that it has a similar arrangement right here. We got a JFET, but this is not in the same place, for one, and for two, it's designed to turn the reverb on and off. That basically grounds out the reverb recovery signal, disabling the reverb for the foot switching. So at first I thought those had something to do with each other, but no. I wouldn't be surprised if that's some sort of global mute circuit, if the amp detects something's wrong. Another op amp buffer. And then finally we hit the phase inverter. And the phase inverter is pretty standard, except for the lack of presence. Dual 47 ends going to the tube coupling. That's standard, that's standard, that's standard. BN, where's our feedback? Is that our feedback there, 47K? Am I seeing this right? Yeah, that off the top of my head does look like about where the feedback would connect. FB, BN. Here it just says BN. So yeah, it's probably the same thing. But wait, that's the feedback. Okay, let me look at the Marshall here. 47 100p, 56. Okay, yeah, that is the feedback, and it has two in series. That's a more conventional feedback, but this with a 10N, that almost looks like a depth, because that's how a depth is implemented. Yeah, actually, I think that's what that is. So basically, this capacitor allows high frequencies to pass, and the feedback will suppress. Again, it's feedback. It's going to cause the phase inverter to suppress whatever frequencies hit it. So if we suppress high frequencies, the phase inverter is going to allow more low frequencies to become amplified. So this combination of resistor and capacitor is pretty much like a depth knob, except this would be bigger on a depth knob, and then that would also give us more range. So this is kind of like a fixed depth to fine tune the low frequency of the phase inverter. And then of course here, this 47K is your conventional that sets how much feedback is actually hitting the circuit, because a 100p isn't going to pass a lot of relevant signal. That basically passes just extreme high end to cause the phase inverter to suppress extreme high end and just take, they call that, I forget, but it's supposed to help suppress the ice picks, like the really high frequencies that hurt your ear. In some cases, you can pull that out to make the amp a little bit brighter, but I've experimented with that. You can barely hear a difference. From there, we have a pretty standard power stage. Anything different from there is Bugera specific. And then of course they're doing that same weird crap with the preamp filaments, where it's a 24 plus 24 volt supply with a little bit of dropping, and then they run them all in series with a center tap, giving effectively 18 volts a side after dropping, so that each coil sees 6 volts. We have our power supply over here on the filament section for the op amps, fully regulated. That's cool. That's going to be nice and quiet. DC heaters for all 3 tubes. DC heaters are a great idea. Like, if you want a quieter amp, just freaking DC the heaters, bud. Buy a circuit, because this one is the non-Infinium model. And then, let's see, bridge rectifier, a pair of 330s. That's pretty hefty. That's a total of 165 UF of initial filtration on the power supply for the main plate. No choke. I've heard of people adding chokes to the 900. Just a dropping resistor to the screen. 100, 100, 50 U for the screen, 47, 33, working our way down the preamp. Filament fusing, artificial center tap with a decoupling capacitor. That's an interesting technique that I see them use. I might try that in some of my builds, because you don't necessarily need actual voltage to hit the chassis for your center tap. You just need a sample of the 60 cycle hum to go in there. So yeah, that's the gist of this circuit. And yeah, I've put it up against the Marshall circuit. Like, it is damn near identical, except for the switching and the choice of op amps and the reverb, obviously. I wouldn't be surprised, in theory, if you could swap out those op amps to 4558s. Well, who's to say the op amps Marshall used sound exactly like the 4558s? That's just what the research says. But I think I've pretty much covered it. That is a circuit analysis of the JCM 900 dual reverb via the Bugera, because I actually found the Bugera schematic that I found a little bit easier to follow. Marshall's very British ways of doing things kind of confuses it, like the diode clipper for the clean channels all the way the frig up here. And you know, the way they have to implement it, because the outputs of the op amp are connected together. So this was a little bit more confusing to read because of the kind of op amps they use. Kind of makes you scratch your head. That's not normally how we would hook up those op amps. Now that I've studied the 1990 circuit, I understand the Marshall circuit a lot better. And it makes me want to try to clone this amp myself. Half because I already have the Mark III. It's only those first 2 gain stages. If you could build the effects pedal, you could build these circuits and just make a couple little perf board modules that I could splice into that amp, and boom, I'd have a JCM 900. And in fact, if you like pedal building and want to dabble in amp building, this would probably be a perfect clone for you, because most of it is like an effects pedal built right in. And I would be extremely freaking curious to tweak on these gain stages here. Like, if we wanted a little bit more depth, we could raise the value of this guy right here, that 47N. In my DOD 250 clones, that's a 5.6. I make it just a little bit more. I've gone as high as a 100, but then I found it did something to the mid. Instead of having the growl, it kind of had more of a moan. Wasn't that much of a fan. I brought the value back down. But this 100K right here, man, if we tweak on that, can we get just a little bit more out of this amp? But if you like this, stay tuned. Circuit analysis shows up in bits and pieces when I talk about and work on other amps. This is one of the few videos where I've actually sat down and walked you through the circuit. That's because it's a more different and fascinating circuit. And let's face it, if you're interested in the Super Lead, the 800, and a lot of other amps, people are talking about it ad nauseum. I don't think a lot of people really give a crap about the 900, which maybe this is a bad reason to make this video, but I don't know. If you like it, stay tuned. I like to work on amps sometimes. Who knows what I'm gonna do next? And I've been talking for a long time. I'm a bit parched.